the data should be large enough, very large data set for both the dependent and independent variable. And for it to be large, or the reason why I want it to be large is that because of the law of large numbers or central limit theorem, the larger the data set is, the more likely that it will be normally distributed. Okay, that's the first one. That's it. So that's the first thing. Apart from that, you also want the errors to be normally distributed. So those are the two conditions I want to use. But the reason the reality is that for the stylized funds of assets or financial assets indicates that they cannot be normally distributed. Whether the data is large or not, cannot be normally distributed. So then there's a problem. We are assuming symmetry for the OLS because if you remember the OLS, it goes through the equation. The equation goes through the middle of the distribution. So it's a mean equation or a mean regression, assuming that the data is normally distributed. But the reality is that that is not the case on the real market because of a number of reasons. First of all, investors or market players are not completely rational, so they don't behave in a way that you can easily predict, in a way that you expect them to, depending on the swings in the market, especially when there's some stress, there's some fear, and there's panic. The reactions do not follow the historical patterns. So that's one. The other reason is that there are some investors who are either long-term investors or short-term investors or medium-term investors. So their behavior, regardless, will tilt towards where their inclination is. And then we also have the fact that investors respond to the market conditions. And those responses are not typically symmetric. Okay. They don't correspond to each other. So you realize that a number of theories have debunked the efficient market hypothesis. So the OLS, for example, is based on the efficient market hypothesis that all investors are rational, but we cannot be sure of that. Now, what happens is that all these irrational behaviors feed into the prices of the assets. And that is why you tend to have tail behavior, or long tails and fat tails in financial assets. And this happens when the market is in stress. So you tend to have a very long tail to the left during bad market times and a very long tail to the right during market booms, so that the middle part will be for normal conditions. And that's how markets typically behave. But if you want to know the asymmetry, whether in this situation the right tail is longer than the left tail or not, then you can compare them. So that's asymmetry. If the two are equal, then you have a normally distributed market price for that asset or returns, no market condition. The chances are they are not the same. In one of the stylized files for assets, it says there's fat tails and leverage effects. So fat tail means one side of the distribution is longer than the other, especially the left. And the leverage effect is that negative returns tend to have more impact than positive returns. And for that reason, it's difficult to have market normality. So if you are using the OLS, it's also difficult for you to understand when the market is doing well and when the market is not doing well. So you are unable to capture the booms and the busts in the market. So we need some other method that can do that. And the method that can do that, one of them is the quantile regression. So the basic idea is that you have, let me see if I can draw this. Let's assume this is the normal distribution of the asset. With the right tail, with the left tail, so LT, this is the right tail. So if it is normally distributed, then the left side and the right side will be the same. It means that the market is doing, it's a very calm market condition, not like the current one we are experiencing. If you look at this, if you take any data set, let's see, you have seen your market, your prices, the data that you presented. If you plot, it will look like this. I'll show you briefly if you plot it as a line plot, not as a cumulative distribution curve. The line plot typically looks like this, which means we have the average or the medium data sets here in the middle. Then you have the smaller values here on the other side, and the larger values here. So if you want to use the OLS, typically what you are going to do is that you go through this middle, and going through this middle leaves all of the rest of the data away. And if you are modeling, you need as much of the data as possible. So that's not a good thing. And given the market conditions, the theories, everything that I've explained, it's not a good idea. So you want to capture as much of the data as possible. What you want to do is to divide the data into many sessions, many portions like this. So you divide them into different portions, which you call quantiles, so that you can model them. So you model this part, this part, this part. So a series of equation, OLS regressions to capture all the data and realize that the relationship between any two of the quantiles are unlikely to be the same, and that is asymmetry. And the fact that they are not the same, that's also a sign of non-linearity. There's no linear relationship between them. This also means that you have been able to capture the declining market conditions on this side, the boom conditions on the right side here, and in the middle, that captures the normal market conditions. I explained to you when we're doing wavelengths of what locality means or localization means. So what we are basically doing is that we are doing localized regression. If you do one OLS for this, that will be a global regression. But if we break them into different quantiles and we model, that will be localized regression. You can say that. So that's the point. The other important point that this addresses is the issue of stationarity. We explain stationarity as over a spectrum where the statistical properties of the asset are the same, i.e. the mean and the variance or standard deviation. Now, chances are, if you take this part here and this part here, then another part here, another part here, the mean and variance here is unlikely to be the same as the mean and variance here, and they are also unlikely to be the same as the mean and variance here. If you have that situation, you have non-stationarity, which you don't have to model across. You always want your series to be stationary, and that's why we define returns in the first place. And we test further with the ADF or PP, KPSS to ensure stationarity. Because if it's not stationary, what is happening is that you are modeling across different market conditions with a single model, and that will render your parameters to be unstable. Because there are structural changes, there are regime switches, there are regime changes that show up over a long period of time in a financial series. Okay. So that presents non-stationarity, which you need to resolve before you model. However, if I'm modeling only here separately, I'm modeling only there separately, and I'm modeling only here separately, each of these chunks or divisions is assumed to be stationary because it's a very small data set. And if we get it to be just a little larger than 30, then it's also normally distributed. Then we solve that problem. Okay. So quantile regression, that's what it does. But it's a general term, quantile regressions. There are specific types of them and they do specific things. Okay. So when you take quantile regression, you only take the different distributions of the independent variable on the dependent variable. You can go further and take the quantiles of the dependent variables on the quantiles of the independent variables. And realize that's a double quantile from each side. And that's called quantile on quantile regression. So that's what we want to do. So this is like the normal distribution curve I gave you. It's typically non-stationary. I have the normal conditions here, the extreme high and extreme low here. So there are a series of distributions that help you to capture the asymmetry in the market. And that's what should be your purpose. I don't believe that you also believe you can use the OLS for any proper statistical work at this point in time. So there are a number of different distributions. There's just a few of them to capture the asymmetry or the fat tails in the data. And the one we are going to look at is the quantile regression. The quantile regression basically divides the distribution into smaller parts and assume normality for them. And the fact that you can they describe different market conditions means that the relationships can be classified into hedge, safe haven, or diversifications or diversifiers. We know that diversification is combining assets with negative relationship or even very small positive relationship so that you benefit from risk reduction. But you can go further into that definition as done by Lucy and Bauer and delineate diversifier from hedge and from safe haven. So that's also one application or inferences we can draw from the method. So what you know as diversification remains the same, negative or small relationship. But now, because you are modeling across different market conditions, you have to specify under which market condition that kind of correlation is. So if it's under normal market conditions, that's fine. You can see it as diversification. So by under normal conditions, it means you are in the middle of the distribution between, let's say, the 70th quantile to the 30th quantile. So 70% of the distribution, or maybe 60%. So that the remaining 40 will be shared across the right tails and the left tails. But if you are looking at it, if you are in a stress market conditions, then you are looking to hedge. So you are looking to protect yourself. So you can look at negative conditions as well. But the most important thing is your safe haven. When you're under very stressed market conditions, you expect one asset to be your hiding place, and they should have a very strong negative correlation, and that is safe haven for you. Okay. So that's one of the main inferences you should be able to make. Okay, so if you look at this equation here, we have for the independent variables, they have the quantiles, which is the theta. So all the independent variables will have their specific quantiles on the dependent variable. So that would be a quantile regression. So as many as they are, you have their quantiles. Okay. But if you want to do for both, okay, it's not here. So if you want to do for both, this is what's going to happen. You're going to have something like this. If you read the papers, I've explained that you're going to have YT. Let me use theta, okay, or phi. So I have YT, maybe phi. That will be the quantiles of the dependent variable. Beta intercept plus, say, beta pi of xt plus gamma theta of ct plus the error term, okay, t3 plus theta error term. So this one is quantile on quantile. So that gives you a complete relationship, and this is semi-parametric. The quantile regression is purely parametric, and we know the weaknesses of parametric distribution. This is semi-parametric, and it's an average of the quantile regression. Because it's semi-parametric, you cannot check the significance of it. What you do, because an average of the quantile regression, you can compare the coefficients of the quantile regression and realize that it's also significant to describe the distribution or not. So that's the quantile on quantile regression. So there are three things. We have the quantiles of the dependent variable, quantiles of the independent variable, and the coefficients. So that will be the three things. So this, if you plot this, you'll be on a 3D plane, which you will see shortly if you have MATLAB available. Okay, so that's the equation part. You can go into the code and see what comes up.